Hello, welcome back. We're going to be talking about stoichiometry. And a stoichiometric equation is the one that relates the moles of the reactants with the number of moles in the products, and it must be balanced. So if you have this equation, you must have, let's say, two sulfurs, in each side, and you will have 2 times 2, 4 plus 2, 6 oxygens, 2 times 3, 6 oxygens in the other side. It has a stoichiometric coefficients. So there will be negative -2, -1 for reactants, and for products it will be positive, and are these numbers, okay? And you can build the stoichiometric ratios. You can say that you have 2 moles of SO3 generated, and per mole over 1 mole of O2 consumed. This could be the other way around, or you can build it with 2 moles of SO3 generated per 2 moles of SO2 consumed, or you can say 2 moles of SO2 consumed per 1 mole of O2 consumed. And the limiting reactant is the one that is present in less than its stoichiometric proportion relatively to the other reactants. So it will be consumed first completely in the reaction if it is completed. And to obtain the ratio of the molar flow rate of each component at the feed, you must divide this guy over the absolute value of the stoichiometric coefficient for all of the reactants, and then compare these values, and the lowest one will correspond to the limiting reactant. In an example, if you feed 150 moles of SO2, 100 moles of O2, and let's say that you have also 376 moles of N2, nitrogen, the limiting reactant will be, so you can do a table where you have the components, the feeds, and the stoichiometric coefficient. Now, the nitrogen is not participating in the reaction, so that's going to be an inert gas, which is not there in the reaction, but it will be in the reactor just to control pressure or something else, right? And then you just divide 150 over 2, 100 over 1. This yields to 75 over and 100. So the one that is less in proportion is the limiting reactant. In this case is SO2, which means that oxygen is in excess. And if you have one in excess, the fractional excess is the ratio of the amount by which the feed exceeds the stoichiometric requirements divided by the stoichiometric requirements. So how much is it in excess over what you actually needed, depending on their limiting reactant. And this is going to be the amount fed minus the stoichiometric relative to the limiting reactant over the stoichiometric. And in our example, you were having a feed of 150 moles of SO2, 100 moles of oxygen. Remember that the limiting reactant was SO2. So if you have 150 moles of SO2 and you need 1 mole of oxygen per 2 moles of SO2, you actually need only 75 moles of oxygen, but then you fed 100. So it means that you are feeding 100, you needed 75, over the 75 that you needed yields to a fractional excess of 0.333 or a 33.3% of excess. The fractional conversion is the one where you have some reactant, and is the ratio of the amount reacted over the amount fed into the reactor. The reactions do not go to 100%. They don't go to completion, but sometimes certain amount of the reactants are not reacting. So if no component is specified, then the fractional conversion is based on the limiting reactant, and it's just the amount of moles reacted over the amount of moles fed. And the amount of moles reacted is the amount of moles that you are going to input minus the amount that is going to go out. So in our same example, if you have a conversion of 70% of the limiting reactant, being that guy SO2, then FSO2 is going to be equal to in minus out over in. That's going to be 0.70 equals 150 minus something that is out over 50, 150. So you can solve for this amount that is going to go out, right? And then you will have 150 minus 0.70 times 150. So the 70% is reacting. So the 30% is going to go out. So the amount that is going to go out in this case is 45 moles of SO2. And then you have the concept of yield, which is the ratio of the moles that of the desired product formed over the moles that would have been formed if the limiting reactant had reacted completely. So in our example, once again, you know that 45 moles of SO2 are going to go out because that's at the 70% of conversion. 30% of the 150 went out, 45 moles. And from these 45 moles, 150 minus 45, 105 reacted. And from the ones that reacted, you know that you need 2 moles of SO2 reacted forms to 4 moles of SO3, okay? So in this case, you're going to be forming 105 moles of SO3. And if you want everything to react ideally, 150 moles of SO2 would have reacted 100%, which goes or leads to 150 moles of SO3 ideally formed. So the yield is going to be the 105 that you actually formed over the 150 that you ideally formed. That's the 70% of yield in our product. So that's it for the basics of stoichiometric.